Good morning. A hearty welcome to one and all present here. Today is the second day of the national webinar on recent development in the characterization of nanomaterials. Today we have with us Professor Chidaranjan Bhattacharya sir of the Department of Chemistry, Assam University, Silchar. It is our pleasure to have sir with us. So, a short introduction will be given by our departmental colleague, Dr. Abhijit Nath. So, sir, please have an introduction of our speaker, sir. Abhijit, sir, please over to you, sir.
Good morning. It's my proud privilege to introduce one of the eminent scholar and excellent teacher of this region, Professor Chiranjan Bhattacharya. Professor Bhattacharya is currently serving as the Professor of Department of Chemistry, Assam University, Silchar. He is also the Dean of Albert Einstein School of Physical Science of Assam University. Sir has obtained his bachelor degree, master degree, and PhD from Northeastern Hill University, Shillong. After completion of his PhD under the guidance of Bhatnagar awardee, renowned Professor Mihir Kanti Choudhury, Sir joined at Guwahati University and teaches there for 5 years, and then he moved to Assam University, Silchar, in the later part of 1996 when we were the student of that department. His widespread area of research includes synthetic inorganic chemistry, soft materials that include liquid crystal, nanoscience, doping of LC with nano, biological sciences, algal template based, metal nanoparticles, carbon nanomaterials from natural sources that includes particularly carbon nanomaterials from plant products, metal oxides, mixed metal oxides, nanoparticles, etc. A total of 18 students got their PhD under his guidance, in which myself is having some privilege to a student, PhD student of himself. 4 students are now pursuing PhD under his supervision. Besides academics, Sir is a very good sports person. Sir was the director of sports board of Assam University for long 12 years from the date of inception of that board. He was the very good opening batsman in the most of the cricket matches. He was also selected for Ranji Trophy trial from Assam in his younger age. Moving again to academics, it's my pleasure to mention that Sir is having more than 100 research publications and over 800 citations in prestigious international and national journals. To mention a few, that includes Journal of American Chemical Society, Journal of Royal Society of Chemistry, Liquid Crystal, Dalton Transactions, Society of Chemistry, LCBR, and Springer journals. I am not able to resist myself without mentioning a few notable achievements of Sir that are: he was the recipient of the most prestigious Overseas Research Student Fellowship in his student time, which was selected by the Board of Vice Chancellors of United Kingdom. Sir was also the Ministry of Human Resource Development, Government of India Leadership and Entrepreneurship Awardee. He is also an assessor of NAC Bangalore to assess different educational institutions in India for NAC grading. Recently, he visited NTU Singapore, that is Nanyang Technological University, which is one of the best top 10 universities of the world. As MHRD empaneled member, Government of India empaneled members to study the different aspects of that university and submit a complete report to the Government of India on that. I'll take a few seconds to mention that he is the pioneer in this region to start work in the field of nanoparticles. It will be incomplete if I do not mention one thing. Sir is a wonderful person, one excellent teacher, a very good laureate. Thank you, sir. Thank you all. Sarvasri madam, please.
Yes, sir. Thank you, Abhijit sir. Now the tax is over to our speaker, sir, Professor Chiranjan Bhattacharya, sir. So, sir, please. Sir?
Yeah. Yeah. Is the slide visible to everyone?
No, sir. Sir, please, sir, screen share, sir. Yes, sir. Yes, sir, it is visible.
Okay. I'm audible?
Yes, sir.
Okay. A very good morning to you all. Dr. Bibhash Dev, Principal of the College, Dr. Rajeshi Pal, IQAC Coordinator, the conveners, Mrs. Sharbasri Nath, Dr. Subhash Debnath, Head Chemistry Department, Krishna Chandra Das, faculties, Dr. T.D. Kanungo, Dr. Avijit Nath, Dr. Jaydeep Pal. First, I thank you all for this unique opportunity to share some aspect of nanomaterial characterization through these webinar. I'm indeed very humbled as well as quite embarrassed by such an elaborate introduction. GC College, a premier institute in the state of Assam, has been very proactive in serving the cause of education, and the chosen theme for the webinar today, I can already see, has attracted a large gathering of science students who are aspiring to contribute in the future. I guess the audience of these webinar has a wide spectrum from undergraduate to advanced researchers. I therefore have planned my talk addressing more basic things and avoiding the technicalities. So just give me a few seconds to rush through the slides. So the topic on which I chose to talk today is the application of electron microscopy to the characterization of nanoparticle. So actually, in the last decade, wherever I used to give a talk on nanomaterials, I used to give some formal definition of nanomaterials because many students and including teachers were not quite aware of what nanomaterials are. People used to just think that nanomaterials are very small materials. But today, I avoid giving any formal definition because they have now intruded our school textbooks. The definitions of nanomaterials have intruded our school textbook. And it is futile to offer a classified definition of nanomaterials. But I had just tried to put up a small, very simple definition of nanomaterials, that you are such a perfect little arrangement of atoms. The invention of the conventional microscope, which we call optical microscope, represented a great step forward for science, particularly in biology and medicine.
Yes.
As better microscopes were built, it was discovered that there exists a limit that cannot be exceeded by optical microscope. This is connected with the wave characteristics of light. Using light waves, it is impossible to distinguish details smaller than the wavelength of the light. The term resolution refers to the distance between two details of an image that can be distinguished. For a conventional microscope using the visible light, the resolution is of the order of about 10 to the power minus 8 cm. If we look at the total electromagnetic wave spectrum, here are the wavelengths of such different rays that we know, starting from the smallest one, gamma rays, to the highest wavelength, the radio waves.
Sir, please click on hide, then you can see the whole screen. Sir, please click on the hide option. Okay, sir.
Okay, just give me a second, because I'm seeing the whole screen. Okay, fine. I'll just try and do it.
Okay, sir. Okay, sir.
Just give me a few seconds. Hide screenটা করার কথা বলছি, আর আবার ফুল স্ক্রিনটা দেখতে পাচ্ছি।
Hello, sir. Yeah.
Okay.
Yeah.
ঠিক আছে?
Yeah. Now it's okay. Okay.
Okay, fine. So I was just referring to the wavelength of the entire electromagnetic spectrum. You can see, starting from the smallest wavelength radiation, that is gamma ray, which is of the wavelength is of the order of 10 to the power minus 12 meter, to that of the highest radio waves of the order of about 1000 meter. Somewhere you can see X-ray occupies a very strategic position just after gamma ray, with a wavelength of about 10 to the power minus 10 meter. So this is very important, actually, when you look at the sizes of the different atoms or atomic nucleus or molecules, etc. So you can see that the atoms also have almost similar dimension as that of the X-ray wavelength. So this is very important for us to realize. See, after X-ray 10 to the power minus 10, there is a small region which is 10 to the power minus 9 meter. Below it is mentioned soft X-ray. There's a mistake here. It should be 10 to the power minus 9 meter, not nanometer. So it's about, so this after X-ray and between ultraviolet, we have a region which is of the order of 10 to the power minus 9 meter, and which is called the nanometer region. And you can see this is also the region between atoms and molecules. So therefore, if you look up between X-ray and ultraviolet, you have a wavelength to probe a region which lies between atoms and bulk molecules. So that is precisely the reason that why we are able to probe nanomaterials with soft X-ray, that is electron beams. So if you look at the different nanoparticles morphology, you have polymeric nanosphere, polymeric nanocapsules, polymeric micelles, liposomes, dendrimers, mesoporous silica nanoparticle, CNTs, inorganic nanoparticles of variety of metals, starting from iron oxide to gold nanoparticle to quantum dot. You have different morphologies, you have different shapes, different sizes, and you can see that they are of the order of nanometer range. So therefore, to probe these morphology, soft X-ray, which is also of the order of nanometer wavelength, are thus ideal scale to probe the nanoparticle. In order to examine the nanoparticle, you cannot choose a much smaller scale, neither you can choose a very big scale. You have to have a compatible scale, and that is why electron beams, which comprise the soft X-ray, are very ideally suited to probe and examine the morphology of nanoparticles. Why then there is the need for electron microscope? The great breakthrough in microscopy came when it was found possible to produce an image of an object using an electron beam. The starting point was the discovery that a magnetic coil can function like an optical lens. A divergent bundle of electrons passing through the coil is focused to a point. A suitable electric field can also act as an electron optical lens. So using a lens of this type, an enlarged image can be obtained of an object irradiated with electron. This is somewhat similar to what the way we obtain image by using normal light, what we call an optical image. So this work with electron was actually carried out at the Technical University of Berlin at the end of the year 1920s. So just allow me to briefly scan the history of electron microscope a little. So light microscopes cannot really resolve structures closer than 200 nanometer. So it is here that electron microscopes have greater resolving power and provides a greater magnification. It can magnify image object from 10,000 times to about 1 lakh times. It can detail the bacteria, viruses, internal cellular structures, molecules, large atoms, and nanomaterials as well. So there are two types of electron microscope, basically. One is transmission electron microscope, and the other is scanning electron microscope. I will restrict today's talk to these two types and give you a kind of overview of these two different types of electron microscopic techniques. So in the electron microscope, the energy source is a beam of electrons. Image is created and viewed on a monitor. TEM utilizes staining procedures prior to use, while SEM adds three-dimensional viewing. So the electron microscope, the beams of electrons are used to produce image, analogous to what light is used to obtain optical image. Wavelength of electron beam is much shorter than light, therefore it results in much higher resolution of the image. Something which I already had explained, that why electron beam is most suitable for probing nanomaterials, smaller size particles. So this is a kind of an image of a typical scanning electron microscope. In transmission electron microscope, electrons are scattered when they pass through the thin section of the specimen. Transmitted electrons, which include unscattered ones, are used to produce image. Denser region in specimen scatter more electrons and appear darker, and that is how an image is procured. So actually, just how small is an atom? Here is the scale. You can see the quarks are very, very small, of the order of 10 to the power minus 18 meter. Then you have the nucleons, which comprises of the protons and neutrons, the inner constituent of an atom. That is of the order of 10 to the power minus 15 meter. Then you have the atomic nucleus, 10 to the power minus 14 meter. Then you have the atom, which is of the order of 10 to the power minus 10 meter. And then when you combine atoms and pack them in a crystal, your dimension is about 10 to the power minus 9 meter. And then from there, you go on to actually the bulk matter, actually, which is macroscopic in system. So we are actually confining ourselves to the size dimension, which is of the order of 10 to the power minus 9 meter, and little above that, so about 1 to 100 nanometer in size. So that just to give you an idea that where does atom or the atomic nucleus or the bulk matter places in the entire size scale. It would not be appropriate for me to just jump on to the discussion of electron microscopy without paying our highest regard to those who helped us develop this particular technique. So several important discoveries are at the back of the development of the electron microscopy. First was, of course, the 1924 discovery of the dual nature of particle, that is the both particle and wave character of a moving particle radiations. And a French physicist, this particular name, I think the students have got them right from their school days, but very often this particular name is not pronounced correctly. So for the students, let me pronounce the correct kind of version. It is Louis de Broglie. So it is not Louis de Broglie. Very often we say, so it is not. The correct pronunciation should be Louis de Broglie, who realized that electron beams have both wave-like and particle-like nature. For this simple but path-breaking discovery, he was awarded the Nobel Prize in Physics later. Came 1931, the German scientists Max Knoll and his student Ernst Ruska built the first experimental transmission electron microscope in Berlin. And in 1933, Ernst Ruska built the first electron microscope that is more powerful than the optical microscope. 1935, Max Knoll, who was his teacher, built the first crude scanning electron microscope. So it was, you can see from 1931, it was the, and from 1935, actually it was the whole arena of electron microscopy was ruled by the student-teacher duo, Max Knoll and Ernst Ruska. And in 1941, the German electrical engineers Manfred von Ardenne and Bodo von Boris patented the electron scanning microscope. So it was from the development of electron microscopy, which practically began from the 1931, was a kind of a domination of the Germans. In 1965, Cambridge Instrument Company produced the first commercial SAM equipment in England, and in 1981, Gerd Binig and Heinrich Roer of IBM's Zurich Research Laboratory invented the STM and produced detailed images of atoms on the surface of a crystal of gold. So that was a very significant year in 1981. We teach our students that atoms are invisible, but the textbooks have to be now rewritten since 1981, that atoms are now being made visible with the invention of this scanning tunneling microscope. So you see, instruments begin to change our whole concept and ideas of basic science as well. In 1985, Binig and his colleague Christopher Gerber produced the first atomic force microscope by attaching a diamond to a piece of gold foil, and then the development continued to 1986 and 1989. I will not go further into the history. Coming back to the electron microscope again, which uses a beam of accelerated electron as a source of illumination similar to the light in optical microscope. There are several different types of electron microscope, but two types are basically very important for the researchers. One is scanning, which produces image of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, producing variety of signals, which are then processed as an image. And in transmission, a beam of electron is actually transmitted through an ultra-thin section of the specimen, which is about little less than 100 nanometer thick, to form an image. So electron microscope is actually a special type of microscope having a high resolution of images, which is capable of magnifying objects in nanometers, which are formed by controlled use of electrons in vacuum captured on a phosphorescent screen. So electron microscope use signals arising from the interaction of an electron beam with the sample to obtain information about structure, morphology, and composition. So here is the beginning of what does an electron microscope do. It gives information about the structure, morphology, and composition. The electron gun generates electrons. Two sets of condenser lenses focus the electron beam on the specimen and then into a thin, tight beam. To move electrons down the column, an accelerating voltage between 100 kV to 1000 kV is actually applied between tungsten filament and anode. The specimen to be examined is made extremely thin, at least 200 times thinner than those used in the optical microscope. Ultra thin sections of 20 to 100 nanometer are cut, which is already placed on the specimen holder. So these are some of the instrumentation aspect, which I will try to only give the salient features. The electronic beam passes through the specimen and electrons are scattered depending upon the thickness or refractive index of different parts of the specimen. The denser region in the specimen scatter more electrons and therefore appear darker in the image, since fewer electrons strike that area of the screen. In contrast, transparent regions are brighter. The electron beam coming out of the specimen passes to the objective lens, which has high power and forms the intermediate magnified image. The ocular lenses then produce the final further magnified image. So electron microscopy as a technique does exploit the interaction between a uniform current density electron beam and a thin sample. When the electron beam reaches the sample, part of the electrons are transmitted while the rest are elastically or inelastically scattered. The magnitude of the interaction depends on several factors, such as size, sample density, and elemental composition. The final image is built with the information acquired from the transmitted electrons. So it is very important, dear students, to remember that image in electron microscopy is obtained from the scattered or the transmitted electrons. Scattered electrons in scanning electron microscopy and in transmitted electrons in transmission electron microscopy. It is the most common technique to analyze nanoparticle size and shape, since it provides not only direct image of the sample, but also the most accurate estimation of the nanoparticle homogeneity. So I could not restrain myself to flash some of the pictures of the stalwart scientists who had contributed immensely to the development of electron microscope, starting from J.J. Thomson, who discovered the electron, and then Louis de Broglie, then Ernst Ruska, who was directly involved in the development of the electron microscope, and his teacher, Max Knoll. If you talk about the electron microscope, the credit for the first discovery of electron microscope should go to Max Knoll and Ernst Ruska, the student and teacher duo. Ernst Ruska is often abbreviated to TEM at the University of Berlin. In short, he is often referred to as TEM by his colleagues. And Max Knoll built the first electron microscope in 1931. For these and subsequent work on the subject, Ernst Ruska was awarded the Nobel Prize for Physics about 55 years later in 1986. Of course, his teacher Max Knoll was left out of the prize. Never mind, because a teacher trained Ernst Ruska. He was himself involved in the discovery of the electron microscope, But for this work, the Nobel Prize actually went to the student Ernst Ruska 55 years later than it was first discovered. So there are some historical anecdote about it. It is my pleasure to share some original photographs of Ernst Ruska and his teacher Max Knoll, who built or who are credited with the development of the first electron microscope in 1931. So the Nobel Prize in Physics in 1986 was awarded to Ernst Ruska for his work done in 1931. He shared the Nobel Prize with Gerd Bienig and Hendrik Rohrer. Ernst Ruska was actually credited for his fundamental work in electron optics and for the design of the first electron microscope. And I must remind that the contribution of his teacher is also there. The other half of the Nobel Prize was awarded jointly for the design of the scanning tunneling microscope. So actually the entire Nobel Prize in Physics in 1986 was dedicated for the development of electron microscope. I shared some of the commemorative postage stamps by different country. Several other countries have published postage stamps. I will run out of slides if I keep showing these postage stamps. For those philatelists, you can perhaps have some visual pleasure by looking into these stamps which mark the discovery of electron microscope. Yeah, actually, you know, this webinar which is being conducted online without being physically meeting, actually we are, because it is the virus which pushed us inside, not allowing us to come and physically meet in a conference. This virus has radically changed all our perspectives of life. And you might be wondering, sir, what is the connect between the virus and the electron microscope? Suddenly, why you are talking about the virus? I must share with you that it is the same discoverer of the electron microscope who first captured the image of a virus in 1931. So if we have any knowledge about virus today, be it coronavirus or be it anything, I think any layman knows the structure and the shape of coronavirus today. But it is because of the development of electron microscope by this German scientist. And they are also credited with the capturing of the first image of a virus. I could have shown that particular image, but I thought that it will be distracting from the basic topic. I will skip this because we don't take much interest in the instrumentation part of the electron microscope. So it has got an electron gun which will produce the electron beam. Then there is lenses and then specimen holder in which the sample is to be placed, and then image viewing or the recording system. I don't go into the details of the parts of electron microscope. About the transmission electron microscope, this is used to view the specimen through which electron can pass, generating a projection image. The TEM is analogous in many ways to the conventional light microscope. TEM is used, among other things, to image the interior of cells, the structure of protein molecules, the organization of molecules in viruses and cytoskeletal filaments, and the arrangement of protein molecules in cell membranes. This is the schematics of the instrumentation in TEM. And you can see that this is precisely the reason why most electron microscope have got a long tubular structure. Unlike all other microscope, because the electron has to flow from a long distance and move several regions and finally reaches the sample. So that is the reason why electron microscope require a kind of a large room and a very long tubular instrumentation type. I will avoid these slides. This is an image of transmission electron microscope. Most important for us to note the copper grid sample holder on which the sample is actually placed for recording the image in TEM. So this is called a grid. Of course, you can see this is kind of a mesh-like structure, and of course, depending on the nature of the sample, we can have a different mesh size grid. Scanning electron microscope is actually a conventional scanning microscopy, depends on the emission of secondary electrons from the surface of a specimen. It has great depth of focus. It provides detailed images of the surfaces of cells. It can also be used for particle counting and size determination and for process control. It is termed a scanning electron microscope because the image is formed by scanning a focused electron beam onto the surface of the specimen in a raster pattern. So the schematics look like similar to that of TEM. I avoid discussing it further. The most important aspect is that how to prepare nanoparticle sample for SAM. So coming to the main aspect of our discussion today, that before a sample can be really observed with SAM, it is often necessary to prepare the sample with additional processing steps to allow the sample to be imaged. This process often makes the sample conductive, more stable in vacuum and under the electron beam, or optimizes the geometry between the sample surface, the electron, and one of the detectors attached to the SAM. In particular, nano-sized materials have the issue that they agglomerate or aggregate, and proper imaging of these samples require special treatment of the samples. The type of sample preparation is dependent on the type of material actually. Conductive nano-sized materials such as metal oxides need little preparation because they are very stable under vacuum. We must note that in electron microscopy, as electron beam is used to capture the image, the entire imaging process is done under a vacuum. So nanomaterials by themselves are quite stable and they are quite conducting, and therefore they give very good SAM images. But not always. Sample preparation for this type of samples require to affix them to a stub by using conductive tape. Because of their conductive nature, they often do not need to be sputter coated with a metal or carbon to aid in dissipation of charge buildup on the surface of the sample. One way of handling aggregation or agglomeration is to disperse the sample in a liquid and spray them onto a substrate. A sonic probe may also be used to break up aggregated or agglomerated samples. Another way is to extract the material from the liquid. In some example, hexane is used in a method to remove titanium dioxide nanoparticle from sunscreen lotion. Conversely, solid inorganic nanomaterials are often poor conductors, and as such may need to be coated to passivate the surface so that electrons from the electron beam are carried from the surface. Other materials such as nickel ferrite metal nanoparticles have been sputter etched to remove the oxide coating on the surface to promote better imaging. Still, other materials such as carbon nanotubes or other organic and polymers have a tendency to be damaged by the electron beam during imaging. So we need to adopt some special care when we try to image carbon nanomaterials or organic nanomaterials. In general, agglomeration and aggregation of the nano-sized materials pose a problem for nanomaterials during imaging or viewing. In addition, a metal or a carbon coating may be applied to allow dissipation of electron buildup on the surface of the sample. The preparation of sample is critical to allow good images and proper particle size analysis of the nano-sized materials. Understanding of the sample is critical to obtain accurate dimension of nano-sized materials. Removal of an emulsion or other liquid that may hamper imaging of the material should aid in particle imaging. Centrifugation can be used to concentrate the solid particles in a solution. After removal, the imaging of the native particles can be conducted. If aggregation of the particle is an issue, use of a sonic probe can aid in disaggregation of the sample. Here are the images of different TAM grids having different mesh size. So if we have some prior idea of the nature of samples, we can actually make some planning to select the grid to be used for TAM. So a suspension of nanoparticle in reagent grade methanol is considered most ideal for the preparation of samples by ultrasonication. Ultrasonication can be done for about 15 minutes prior to the sampling. Grid types were manually prepared by placing 10 microliter of the suspension on the grid and allowing it to dry. These samples are then placed in a TAM storage box after drying. Instead of methanol, other solvents, including water, may be used depending on the nature of the samples and dispersibility in it. Nowadays, even robots are being used actually to prepare the samples. The grid is actually transferred automatically by the robot. So these systems have come up. The images are then analyzed to extract matrix on the size, shape, and morphology of the nanoparticles. The system has been used to characterize plasmonically active nanomaterials. So the whole element of human or manual interface is removed nowadays in some of the modern version of the electron microscopic instruments. So actually the robotics as a science is coming up in a big way, we all know, and it is also integrated in the use of electron microscopy that avoids the human interface. The restriction of using a unique TAM grid for every sample imposes a major bottleneck on imaging. The surface area of a typical electron microscope specimen grid is such that there are potentially on the order of 1 lakh high magnification targets available for imaging. Given that the size range of nanoparticle is typically of the order of 100 nanometer or so, and if the particles are reasonably distributed with sufficient, therefore to procure an image of about 500 to 1000 particles with sufficient resolution to accurately extract the detailed structural characteristics of the particle, it is a challenge. Actually, image of any nanoparticle sample can be acquired from an area of the grid that only represents 0.002% of the available space on the grid. So with this idea tentative idea about the sample preparation for SAM and TEM, I have avoided being technical. I thought that it would be more appropriate to take you through a guided virtual tour to SAM and TEM images of different nanoparticles accessed through variety of synthetic routes, including greener ones. So get ready for this virtual tour to SAM and TEM images of different types of nanoparticles. Here are some palladium nanoparticles, which was synthesized using a chemical SID-mediated method. You can see the SAM images are so very clear. The roughly the polygonal shapes are visible from the SAM images, though TEM image is not very clear. So sometimes for certain types of particles, SAM images could be better, and for some, in some occasion, TEM images could be better. You can see that there is a bar, length bar in each of these images. And for the student and young researcher, I must tell you that whenever you write an article for publication and give SAMTEM images, never forget to use the length bar. Otherwise, the picture carries no meaning. So therefore, because the length bar gives us an idea about the dimension of the particles. So very beautiful pictures of the more or less disaggregated nanoparticles of palladium are visible. So this we have taken from the source of Journal of Physical Chemistry journal published in 2010. This is also palladium, but now this time you have nanocube type of structure, and this process was particles were synthesized using ascorbic acid. You can see a beautiful SAM images. It gives a kind of a mosaic texture, and the TEM image, and also the SAM image clearly tells the cubic type structures, and the TEM image also supports that. So the shapes and the nature of the clearly separated particles are known from the TEM and SAM images both. So this work was published in 2015. This is about silver nanoparticle, where nanospheres, silver nanowares, silver nanocubes have been shown. You can see the TEM images are give somewhat much better clarity, TEM images, than the SAM images, but in combination, both TEM and SAM give much information. In the inset of the TEM images, you can see that some pictures are there showing simulated molecular simulated structures of the nanoparticles. Either it is a polygonal shape or a tubular shape or cubical shape, but these are not the image taken by TEM. These are actually simulated images based on the TEM and SAM images, which are put inside as an inset to understand what actually the structure look like. So we can see that how beautifully we can actually decipher nanospheres from nanowares and nanocubes based on both TEM and SAM images. This work was published just last year, and we have taken these images from that particular paper on ACS applied energy matter. This is about silver nanoflower. We just talked about nanosphere, nanowares, but now you can see beautiful flower-like textures of silver nanoparticles. The SAM image as well as the TEM image clearly reveals the flower-like shapes of these particles. This is also published in the same journal in 2018. it is a treat to the eyes to see these beautiful images of nanoparticles. But for electron microscopy, we would not have access to this beautiful nano world. This is an image of gold, silver, and gold-silver alloy nanoparticle, green synthesized using extract of Hypocrater informis. In fact, we also have synthesized in our laboratory gold particles, silver nanoparticles, and gold and silver alloy nanoparticle using a red algae, but I have not included the images of these here because the thing is not published, and I am yet to process the results, but we got these results during the lockdown. So it's very beautiful images of gold nanoparticle, silver nanoparticle, and the alloy nanoparticle were obtained using red algae. So you can see the SAM and TEM images. The interpretation of the images are getting slightly more challenging sometime. But this is a work which was published in 2016. Another very beautiful picture of a green synthesized nickel oxide nanoparticle using a leaf extract. You can see more or less spherical shaped nickel oxide nanoparticles published in Applied Organometallic Chemistry. Going further, this is a copper oxide nanoparticle, green synthesized. We can see a very beautiful picture in the SAM image. TEM images are not very, very clear. It shows more agglomeration, but SAM images clearly tells us the nature of the morphological aspect of these nanoparticles. This was published in RSC Advance in 2014, from where we have taken these pictures. Another very unique morphology can be seen of tin oxide nanoparticle. And we can see that actually spikes-like structures coming out of the whole thing. So these tin oxides are also called nanospikes. This is synthesized using hydrothermal route. This is a 2011 publication in Journal of Material Chemistry. Zinc oxide nanorods, beautiful images synthesized via microwave assisted solvothermal method, published in Nanomaterial Nanotechnology. You can see both SAM image as well as TEM image give ample evidence for rod-like structures of these nanoparticles. One can in fact calculate the length of such nanorods also from these images. This is about zinc sulfide nanoparticles synthesized using chemical methods. TEM images are not very clear, shows some aggregation, but from the SAM image, it is very clear that they are more or less spherical shape. Chemical physics, material chemical physics in 2015. Yeah, a very beautiful image again of bismuth sulfide nanoparticle synthesized via hydrothermal methods. You can see each of these nanoflowers growing in SAM image as well as in TEM image. 2018 publication in Advanced Powder Technology. Beautiful application of both SAM and TEM shown in the interpretation of the morphology of newer nanoparticles. This is about copper sulfide nanoparticles. SAM images at different magnification. you can refer to the image B and E of SAM image, which gives more clarity of the particles. In B, it appears kind of a sphere type, but when you actually increase the magnification, you can see that each of these spheres actually have got projected rods coming out from a central point. So beautiful SAM images. TEM images also support the SAM images, but they are not so very clear. But together, they tell a huge story of the morphology of this dandelion-like copper sulfide nanoparticle. Published in Chemical Physics Chemistry, 2015. This is about core shell copper oxide zinc oxide nanocomposite synthesized using co-precipitation method. It is a publication in 2018. This is about reduced graphene oxide, iron oxide nanocomposite. So not only about simple pure nanomaterials, one can actually image the nanocomposites also, synthesized using hydrothermal methods. You can see clear SAM images showing the ball-like structure of the composites, though TEM images are not very clear. This was published in 2014, Journal of Material Science and Technology. I've included some images from a published paper in Polymers 2014 of carbon nanotubes. You can see single-walled carbon nanotubes, SAM image. TEM image is also supportive of that. And then one can see in the bottom picture of a multi-walled carbon nanotubes. So you can see that how, with the help of both these techniques, SAM and TEM, it is really possible to ascertain whether such nanotubes are single-walled or multi-walled. So a very beautiful interpretation of morphological features is possible using this electron microscopic technique. Some more composites, core shell type structures. You have gold outside, palladium inside, gold outside, platinum inside, core shell nanoparticle. So you can see that in the TEM images, picture A, you can see, or even you can see that because of the darkness, darker region and the lighter region, you can see that we can actually decipher picture A and see that it is a kind of a core shell structure. Inside, some metallic density is there, and outside, the metallic density is scattered. So from this kind of features, black and white features, differing region of darkness and light, one can actually conclude about the formation of core shell structures. Though from the images at B and E, it is not very clear that they are core shell. But from the ABC, you can actually decipher that they are indeed core shell-like structures. This was published in 2012, Journal of Material Chemistry. This is a heterogeneous silver-copper bimetallic monolith. So this was also, the structure morphology was also probed by SAM and TEM. This is about copper and silica core shell nanoparticle. So this is a more or less spherical shaped composites. Scientific Reports 2014 publication. SAM and TEM image of a organic functionalized silica polymer core shell nanoparticle, perfect spheres. Images apart, you can appreciate the beauty as if someone has actually drawn using a compass some perfect circles. But actually it is the nature which has made this spontaneous synthesis of nanoparticles, spherical nanoparticles. Perfect. And in the SAM images, you can see the images appear like, rasgullas with full of juices ready to be taken inside. See, the picture is so beautiful. It reminds in your mind a lot of different images. And to my mind, it reminds me of the sweet rasgulla. Actually, it's full of juice inside. So you can see that electron microscope can probe deeper inside such nanoparticle structures and bring about the morphological features so very clearly. Silica and iron chip-based nanohybrid. Again, you see, you have multiple components in these nanoparticles. So the pictures, the images are not very clear, but in the same picture, the features are more or less clear. This was a very, very recent paper from which we have taken this image, just to tell you that you have got three components, two metal oxides and one chip-based ligand to have the nanohybrids. Naphthyl grafted iron oxide nanoparticle. Again, you have got beautiful spherical images in the SAM and TEM, published in 2018, Microchemica ECTA. Then about zinc oxide carbon quantum dot nanocomposites. I'm trying to show you a variety of nanoparticles and how their image look like. But sometimes, because of the innate nature of the samples, the images are not very, very clear. But even then, combined SAM and TEM approach give us a kind of a clear idea about the nature of the hybrid nanomaterial. This was published in Journal of Colloid and Interface Science, 2016. Graphene oxide and reduced graphene oxide, SAM and TEM images. You can see flake-like structures of graphene oxide and reduced graphene oxides so very clearly in SAM. And TEM also, it is visible. 2019 publications. Further images of graphene oxide and graphene oxide silver nanoparticle composites synthesized using cyclodextrin. Then manganese sulfide and reduced graphene oxide nanohybrid. 2017 publications. TEM images are more clear. So basically, therefore, we can continue showing you images, but somewhere I must put a full stop. And TEM and STEM image, though I'm not talking about STEM here, images provide more localized information. And from TEM and STEM image at proper magnification, one can retrieve the size distribution as well, directly by simply counting the particles with different size. For nanomaterials, morphology indicate the shape and surface facets. Nanoparticles, zero-dimensional, nanorod, nanowire, nanotube, one-dimensional, and nanoplates and nanosheets, two-dimensional, represent distinct shape of nanocrystal, which consequently enables the control of the activity or stability of catalysts. For a large nanocrystal with regular shape, the morphological information of shape can be obtained from the SAM image or coherent synchrotron X-ray technique. Due to SAM's limited resolution, the shape of a small nanocrystal can only be resolved better with TEM. So TEM images represent a 2D projection of a 3D object through a dynamical interference process. Although the process of the electron beam scattering is much more complicated than the process in optical microscopy, after proper data analysis, that is reconstruction, the 3D morphology, shape, orientation, facets, etc. of nanoparticles with regular shape can be directly determined from high-resolution TEM imaging from one or several projections. So basically, if we would like to put SEM versus TEM, for SEM, sample must be conductive or else it will burn. So over 300 times magnification may be possible in scanning electron microscope. In transmission electron microscope, sample must be very, very thin, else it won't project a recognizable image. It is just two-dimensional, and the magnification can be achieved up to 1 million times in TEM. So these are some pros and cons of using SEM and TEM, but depending on a given sample type, both this technique can be very useful with certain merits and demerits taken. I have come to the end of the talk almost. I do not have much to share on this, but just to share with you that in science, if you do not make mistakes, you are doing it wrong. And if you do not correct those mistakes, you are doing it really wrong. And if you can't accept that you are mistaken, you are not doing it at all. This was a quote I obtained, and I do not know who has written it because it is mentioned as anonymous, but I was so attracted to this quote that I could not resist to share with you all this particular quote. Having come to the end of this talk, I must express my deepest thank to the Department of Chemistry, the GC College in general, and the IQAC for actually giving me an opportunity to share this dais online with so many students participating. It really gave me a lot of happiness to be online and interacting with so many people around on a topic which is so very frontier. It really have given me a lot of happiness. I'll be here for any queries, if any I can take. Thank you so much. Over to the coordinator.
Thank you, sir, for your inspiring and valuable speech. Sir, we are really honored to have you in this auspicious occasion. Thank you, sir. Now there will be a question answer session. It will be taken over by our Subhas sir. Subhas sir, please. Question answer session.
Sir, yes, sir.
Yes, yes.
Sir, please stop the
Sharing.
share. So let me
Yeah,
get
yeah, yeah.
quick questions, sir.
Yeah, yeah, right.
So there are a few questions here. Sir, first question is a very interesting one. It
Yes.
is asked by K.K. Mohan Reddy.
Okay.
Can coronavirus structure be detected by electron microscopy? Can
Okay.
coronavirus structure
Yeah.
can be detected by electron microscopy?
Yeah, yeah. Okay. A very good question indeed. Actually, the dimension of coronavirus is also of the nanometer scale. In fact, most of the virus have got nanometer dimensions. And if you would note that India has already in the last couple of months has successfully imaged using electron microscopy the coronavirus. So this has already been reported from India only. Electron microscopy has been profitably used to picture the coronavirus, and our Indian lab has done it already. Very good question. Thank you.
Thank you, sir. Thank you very much. Few more questions are there. So, sir,
Yeah, please. Yeah.
one question has come from Dia Coach. So, is green made by copper? If it is so, why? And followed by that, we will ask another question. Are all the colloids nanoparticles?
Yeah. Okay. Can you repeat the first question? I
First
could
part
not get it.
is green made by copper?
Is green
Grid.
grid?
Grid.
Yeah. TEM grids are made of copper actually. TEM grids are made of copper. Even the SAM stub on which the sample is placed in scanning electron microscope is also made of copper. So that is why when we record ADAX along with SAM and TEM image, we get signals for copper. So actually copper is used in both scanning and transmission electron microscopy because copper is highly conducting material and the images are actually procured from scattered or transmitted electrons. So if the substance is not sufficiently conducting, then we will not get a good image. That is the reason why stubs or the grid are made of copper. And yes, colloids, nanoparticles, it's very simple. All colloids are not nanoparticles. Colloids can have bigger size dimensions, but you can have colloids in the nano dimension also. So they are called nanocolloids. So if the colloidal particle size are of the nanometer dimension, then you can have nanocolloids. But you can have colloids which are of macroscopic size also. Colloidal particles may not be always nanoparticles. So all nanoparticles are also not colloids, but in a way people say that nanoparticles are colloid-like structures, but all colloids are not nanoparticles.
Question.
Like all proteins are not enzymes, only those which catalyzes reactions, they are called enzymes. But all enzymes are proteins.
Okay, sir. Another question is
Yeah.
Prakash Kurmi.
Yeah.
What do we mean by simulated image and how it can be achieved in case of SAM?
Okay. Actually, these the data, electron scattering data, which the machine collects, because when the electrons impinge on the sample, then electrons are backscattered from the sample. These electrons are actually quantitatively collected by the machine, and these data can be processed to interpret what composition, what elements are there in the sample, plus they can be actually processed by using a software to sort of simulate images. So this is actually a software processing of the data which is collected. Data means backscattered X-ray from the sample. So simulation means it is actually like, for example, molecular structures we simulate. So it is a kind of a software based approach for generating structures. These are not direct images of the samples.
Okay, sir.
One of the very popular software in electron microscopy is J software, J image software, for the information of the students. Yeah.
How can we measure the structure and dimension of sample from the image of SAMTEM? I think you have already explained this part.
No, but let me take it because that is also very important.
Yes,
I have explained. Usually, a kind of a length bar is there in the image that can be used, but they do not really give precise uh, size dimensions. For in order to obtain size dimension, precise size dimension, one must resort to XRD. TEM and SEM gives a kind of a somewhat broader idea about the size dimension, but for precise size dimension, one should resort to powder XRD.
okay, sir. Thank you, sir. Another question has come just now. So, sir, how will be nanoparticle helpful in medical treatment?
Okay.
This is a
Anyway,
broader area, sir.
broader area, fine, I will take it. Actually, there are so many papers on the uses of nanoparticle in medical treatment. Already, some nanoparticles like silver nanoparticles are being used for medical treatment. Some of the skin vestments or wound healing bandages uses silver nanoparticle, because silver nanoparticles have got antioxidant and antimicrobial properties. So they are being used in micro bandages and in ointments, and also in some sunscreen lotions. So plus nanoparticles can help build nano medical device for imaging. Cellular images can be obtained. So this silver nanoparticle has come in a big way in the nanoparticle in a medical field. Also, gold nanoparticle has also found extensive application in the domain of medical science uh, for variety, including cancer treatment, which is called photodynamic therapy, PDT. So nanoparticle has come in a big way, and it is believed that the future of medical science will be predominated by the nanoparticle chemistry, physics, and biology. And that is why if you turn the journal, any science journal today, physics or biology or chemistry, actually more than 75% of articles are dedicated to nanoscience and nanotechnology. So therefore we like it or we debate about it, but nanoparticles have come to stay in a big way, though the health aspect of the nanoparticles to environment and also to the living systems have not been actually probed to that extent, because the developments in nanoscience is so very fast taking place. The time for research into the adverse effect of such nanoparticles are not really being allowed. So I think this is one very important dimension which is to be addressed by the new generation researcher, that how safe nanoparticles will be, because they are created by man, they do not naturally exist in the system. So it is for the new generation to see and consider how it is going to be much more useful in the coming days.
Okay, thank you, sir. Sir, one question is come from
Okay.
our beloved Tushar Kananda sir, who we lovingly call DDA sir.
Okay.
Sir, want to know, does a neurotoxin apply to nova skin of Russia is a nanoparticle? Does
Okay.
electron microscope is used to detect it in Germany?
Okay, you see, since it is Tushar Dev Kanungo, I will try to bat this bouncer in a different way, because I have played him in the cricket field, and here also he has come with a bouncer, I must admit. And I always used to leave some of the balls and deliveries of Tushar in the field, cricket field. And today also I chose to leave this delivery because I have no idea about this neurotoxin, what he is referring to. Maybe I can get back to the internet and find out, but I really have no idea. So I will leave this delivery of Tushar as a bouncer. I really do not want to hit it for a 6. But thank you. I will try to know about it, but I have no
Thank you, sir.
idea.
Thank you.
Thank you very much, sir. It's a very enlightening
Thank you, sir.
lecture, sir.
Thank you for nice
Enjoyed it
words.
very much. Really, it's a very good one, sir.
Thank you. Thank you. I enjoyed actually very much.
Thank you,
Particularly,
sir.
yeah, Sharbosri,
Yeah,
Subhash, Krishna.
so, sir, now the vote of
Thank you,
thanks
sir.
given by our Shubhash,
Thank
sir.
you.
Sir, please.
Thank you.
Sir, sir, actually, we are very much pleased to have you in our GC College platform in this webinar. We planned actually to make a successful seminar type, but due to this pandemic, we could not manage it. Anyway, we are very thankful, sir, for your kind cooperation and giving us such a valuable time and enlighten us, our participants. So thank you very much, sir. I offer my thanks to our principal, sir, Dr. Vivash, sir, for providing us such platform, e-academia, in coordination with the IQ system. I also thank our coordinator, madam, IQC coordinator, madam, Dr. Rajashri Pal, madam. I also thank our HOD sir, Mr. Krishna Chandra Das, and our convener, madam, Mrs. Sarosina, and our mentor, sir, Dr. Tushar Kanpur, sir, for their help and cooperation to successfully complete this webinar. Thank you very much.
Once again, I thank the speaker of the day and all participants. So, all participants, you must fill up the feedback form given in the chat box. Stay safe, stay healthy. The session is formally over. Thank you, sir.
Thank you. Thank you, everyone. Thank you.
Thank you,
Thank
sir.
Thank you, sir.
Thank you. Thank you,
thank
Krishna.